Welcome to today's GEOTOP seminar. Today we'll have the pleasure of having Eric Goubault from École Polytechnique tell us about directed homology theories based on bimodules on algebras. So the floor is yours.
Okay, thanks a lot, Pablo. And hello, everyone. So I'm going to try to construct algebraic invariants for directed spaces. So these directed spaces, I'm going to introduce them very quickly. They are just topological spaces which have a distinguished set of, or subset or subtopological space of continuous paths on them. So dx is included in this space of continuous paths from continuous maps from 0, 1 to x. And this distinguished set of continuous paths is called directed paths, right? So it obeys some laws. Of course, you need to be able to compose directed paths and still be a directed path. Constant paths should be directed, and you can reparameterize them using increasing maps from 0, 1 to 0, 1, of course. And these directed spaces, they model a number of interesting situations for several kinds of applications. So originally, this started in concurrency theory, where you had multi-agent systems, different processes running all together. And the sort of, so the space of states would be a higher dimensional topological space of some kind. But then what we're interested in these concurrent processes or multi-agent systems is paths that always make progress for each process, for each multi-agent. So it defines a cone of future directions, which is locally Euclidean. It's really some kind of ortant into Rn, where n is the number of agents. So it's pictured here with two agents. You have these directions on the arrows, and the cell goes, is locally ordered as this positive ortant, positive quadrant in that case. And you can only move paths, so directed paths we're considering are only the ones which go in this positive cone, the positive quadrant at each point, okay? So that's for concurrency. I won't elaborate on that. For control systems, just to let you know, it's of interest because most control systems, they can be modeled as differential inclusions. So on some kind of manifold of configuration states, you would pick up some subcone, generally closed convex subcone at each point of the tangent space, in which your trajectories should lie. The derivatives of your trajectories should be inside that cone. And this restricts the paths you're going to consider. And this is going to be your dx, your set of directed paths. And indeed, you'd like to understand or classify these directed spaces with some sort of computable invariant. So what comes to mind immediately is to try to define some kind of homology theory, homology invariance, and that's been eluding us for quite a while. We've been trying many things over the last 30 years. We have partial answers and everything. And this is an attempt to sort of reconcile some of these and having right properties, whatever. Just to recap things, of course, if I'm looking at this punctured space, so these are two holes in gray. This is squared minus these two holes. And of course, the first homology would just be, the first homology group would just be Z2. There are two generators given by the two holes. And this is going to be an invariant under classical homeomorphism, of course, of these topological spaces. And these classical homology theories, like singular simplicial sets, simplicial homology theories, for instance, they're constructed from, let's say, singular models, simplicial set models, like singular simplicial sets, with a construction of chain complex out of them, taking kernels and images of boundaries, constructing them, and the property of the algebraic properties of abelian categories, such as the ones that are taken as coefficients in general, like Z here. So the abelian groups that are taken as coefficients make it possible to have very nice features, exact sequences, Mayer-Vietoris, and relative homology groups, and so it's very convenient for directed calculations. And we want to mimic that, but then the problem is that directed homeomorphisms, so homeomorphisms which respect the cones, the future cones, or the subspace of directed paths, it's much finer as an equivalence than homeomorphism. And so you cannot count cycles modulo boundaries. You cannot use ordinary homology to classify them. You need to sort of count directed paths and higher directed paths of some sorts. So let me just show you why. So let's consider once again this square, which is punctured by two gray squares. And so this one is the same as this one, classically speaking. It's homeomorphic. It just the holes have been put in different places, but in ordinary topology, these are the same two topological spaces. They have Z2 as H1 as first homology group. Whereas if you look at this as a directed space, that one as well, with the quadrant, positive quadrant as the cone of future for all directed paths. So directed paths should be increasing in all coordinates, in the two coordinates, like the red direct paths here. Then there are essentially different spaces. And it's easy to see because if you just look at maximal dipaths, the ones from the origin to the endpoints, then you have three, which are pictured here for this space, three modulo deformation, right? Modulo some notion of directed homotopy through directed paths. Whereas for this one, you have four directed paths modulo directed homotopy, right? So this is not going to be dihomomorphic because this is actually quite obviously this set of directed paths modulo dihomotopy is going to be an invariant dihomomorphism. So we need to cook up some new sort of homology theory based not on cycles, but on directed paths and higher directed paths. And we want to have a right algebra for that. But then the algebra is not going to be so simple to get. Just think of this space. So that's just a hollow cube, just S2, topological speaking. And then still it's going to be, the cone still is going to be an orthant, right? It's positive. So you're going to follow project out on these directions on the three axes to be in the positive cone. And if you look at the two red paths here, going from that point to that point, then these are not going to be dihomotopic. These are homotopic, right? You can deform one to another going through ordinary paths, but they're not going to be deformable through directed paths, because at some point you need to go through this deformation from the top one to the lower one through non-ordered, not directed paths. So this will create something which is in the corresponding H1, directed H1, as we're going to see. And algebraically, it's going to be a bit complicated with respect to the classical abelian coefficients, in that if you precompose these two paths by this red arrow and postcompose with that other red arrow, then this upper composite is going to be dihomotopic to the lower one, okay? So it's not going to be an algebra in which you can cancel out products, okay? It's going to be non-regular in many ways, okay? But still, can we attain exact sequences? Can we do something similar as the classical simplicial homology? And the answer is yes. So there's been several approaches. So there's one to which I won't have time to compare, but you have the same sort of contents in many ways. So one which we introduced using natural systems that I was reaching. There's also approaches in semi-modules, so homology and characteristic one, which is a direct kind of homology theory, and which has some links, but has less sort of exact sequences as we do. And I did propose recently a semi-abelian kind of approach using associative algebras as coefficients, which tells you quite a lot and has some exact sequences, but not as much as in that current framework. And of course, there's been many other leads that we've been trying for quite a while. Okay, so what we'll be using is actually classical associative algebra, not just the one I just mentioned with semi-abelian, the category, semi-abelian category of associative algebras. I'll use bimodules of algebras. There'll be a link to persistence homology. So I'll use persistence modules. You will be able to ask me questions on that. I won't describe so much of it today. You recognize that if you are doing persistence modules anyway. And we'll have most exact sequences. Okay. Okay, so I'm not going to cover everything. I'm trying just to define it and show you one exact sequence at least. And the story goes as follows. You would start with one particular combinatorial model of directed space, which is semi-cubical or precubical sets. That's going to be the most convenient presentation. So it's like, you should think of it as like starting with ordinary simplicial sets and trying to define some singular, some simplicial homology theory, right? But we're starting with cubical sets or precubical sets instead. So precubical sets are just made up of n cells which are n cubes, n-dimensional cubes, and you would have two families of boundaries for these n-dimensional cubes. The start one with the 0 on top of the operator, and the n ones with the 1 on top of the operators. So you have two n boundaries for an n cube as n-1 cubes. And you'll have a commutation relation between these boundary operators, which is very much the same as for simplicial sets, right? You recognize it. So I won't be considering degeneracies of any kind. Anyway, it won't be necessary as such for homology, although it would be for a less restricted class of cubical of shapes. Okay, let me not comment on that today. So of course, this is a 2-cell, and you have these two starting boundaries with the 0 on top as a superscript. And the end boundaries would be these two edges, and the commutation relation just tells you that this is a common point. I mean, the end of the beginning is somehow the beginning of the end, right? And it shows you, it gives you the combinatorics of n sets. Okay, and there's a category of precubical sets with the obvious morphisms, and it's a presheaf category. You have a geometric realization, so you have a geometric realization as a classical kind extension where you represent each abstract n cell by a concrete n-dimensional cube, unit cube, for instance, in Rn, right? And these are just glued together, respecting the order given by the different boundary maps, okay? But now we want to count directed paths and higher paths, not just loops, right? We don't have always interesting directed loops, and that will be constructed on based on the construction by Krzysztof Zielinski. So I'll just recap a few things and give examples. I mean, so the idea is really to define combinatorially what are directed paths and higher directed paths. And for the class of cubical sets I'm interested in today, it's enough to consider these given sort of tame paths, which are just sequences of cubes indexed by 2 points, V and W. So intuitively, this sequence of cube is just going to represent a concatenation of cubes along points, endpoints, going from vertex V to vertex W. So when this sequence is empty, you must have V is equal to W. This represents a constant path on vertex V. When it's not empty, you just have to have the iterated boundary, the iterated start boundary of C1, which is V, the iterated end boundary of CL, the last cube in your sequence, to be W, and the iterated end of CI is going to be the iterated beginning of CI plus 1. So it's just cubes glued along their endpoints. So the sequence of dimensions of these cubes, C1 to Cn, is going to be called the type of this cube chain. And the dimension of the cube chain itself is going to be computed as follows. It's going to be the sum of the dimension of the individual cubes within that cube chain minus the number of cubes. I'll just show you examples right now, okay? So here are two simple cubical sets of dimension 2. So C and D are two cells, two squares, filling squares, E and F as well. And you have the underlying graph of this precubical set. So what you can see very easily from the definition is that what we call zero cube chains, they're just directed paths from V to W, right? It's just a sequence of one cube, so a sequence of edges which are which are glued, sorry, by their endpoints, the end vertices. Okay, so this is this red thing is the sequence IJLJ, IJLJG, sorry, is going to be a zero cube chain, and many others, of course. So one cube chains, if you think of it as the dimension of a cube chain is the sum of the dimension of the cubes minus the length and minus the number of the cubes. The only way you can get dimension one is that you have a two cell and the rest is one cells. So one cube chains are going to be just the whiskering or the pre-composition or post-composition by directed paths of a two cell, right? Okay, so C followed by F and G is going to be a one cube chain, okay, as well as others. And so I'm not going to go into combinatorial formulas, but it's still in some of the papers of Professor Zimensky. You can generate from these cube chains a chain complex, right, which I call Ri plus 1 of X, which is a free R module given some ring R, generated by all cube chains of dimension I. And there's a boundary operator, which has this rather complicated formula. These are boundary maps, which are defined later, but which you don't need to know exactly, which gives you a chain complex structure on this free R module. So it just means that delta square is equal to 0. And furthermore, this chain complex, it agrees with the endpoints of the cube chains you're considering. That is, if you're considering cube chains going from V to W, then delta of this cube chain is going to be a cube chain of lower dimension. It's going to go still from V to W. Okay, so let me not define precisely the boundary operators. I'm going to show you some basic pictures of what they're computing. The main property you have to understand, still proved by Christoph Zimensky, is that for some particular subclass of precubical sets, which is still interesting enough for my applications, concurrency or control, which has this property, then the homology of the chain complex I've just defined on cube chains is isomorphic to the homology of the trace space or the topological spaces, the topological space of directed paths of the geometric realization of my precubical sets from V to W. Okay, so if I take the chain complex of my cube chains that go from V to W, using this boundary operator I had on the slide before, then computing the homology as usual of this chain complex, I'm going to exactly know the topology of this topological space of directed paths from V to W of the geometric realization, right? So that's a very important step towards understanding and classifying the directed space, of course. So just to give you some intuition about how it goes, that's a one cube chain, that's a KFB, F is a two cell. And so the boundary of this one cube chain KFB is going to be KDEB minus KCAB. So it's really the geometric boundary as a difference of the two two directed paths at the boundary of this one cube chain, right? So it's a surface, and you just take the difference between the two directed boundaries of this very simple surface. Okay, for a 3-cube, you have to understand what are the different 0 cube chains and 1 cube chains. So the 0 cube chains that just directed paths, as I told you. So the maximum ones from beginning to end, there are just 6 of them, the ones that are pictured here. And the 1 cube chains are going to be pre and post compositions of just 1 square. So you have also 6 of them. So you have this square pre-composed by that arrow. You have that square post-composed with that arrow. and so on. So you have all sort of, going around the faces of the cube using this particular combinatorial bypass. And as I've just showed you, for instance, the boundary of this one is just going to be the geometric boundary of the surface. So that directed path minus that directed path, okay? And then there's a unique two-cube chain, which is the three cell itself. So it's length 1 and it has dimension 3. So 3 minus 1 is 2. So as a cube chain, it's of dimension 2. And if you use the boundary computations that you cannot possibly have looked at in my presentation, right? I mean, I just give you the formula right there. The boundary of this cube chain, which is just made of the cube itself, is just going to be the alternate sum of the 6 one cube chains you had before. So basically, it's going to be so the boundary of the cube itself is going to be the alternate sum of these 3 surfaces, right? So it just gives you a way to see the boundary of the sphere in some combinatorial manner using only directed surfaces. Okay. So now, and I'm going to stop right after this sort of abstract to see if you have questions so far. And I'll just click on a few things to explain more in details, a few selected items. Now I'm going to go one step ahead. So now I'm going to say, it's not enough to know the homology using some nice chain complex. So it's not enough to know the homology of the trace of the direct path between a pair of given endpoints. I want to know what happens if I move around the endpoints. And to do so, I'm going to change the coefficients of the homology theorem I'm going to use. So before I had just a ring as a coefficient, right? But I will change that to use the path algebra as coefficient. So I will need to define the path algebra of a precubical set, which is going to be the classical path algebra of the underlying quiver. Then I'll be using these as coefficients. So I'll be defining modules or bimodules over this path algebra. So and particularly I'll be interested in bimodules of cube chains of dimension I. I'll show that these are bimodules. The action of the path algebra will be whiskering on these I cube chains, pre and post compositions. I'll show that the boundary operator that I had defined just on the chain complex on ordinary modules on rings is actually defining a chain complex of bimodules on the path algebra. And then I can define homology bimodules over the path algebra because I mean bimodules over a given algebra forms an abelian category. So I can just quotient kernel over image of that boundary operator seen as an operator between bimodules over the path algebra. And then for those who know persistence modules, these define persistence modules. This is linked to the former proposal of natural homology. And what I'm really going into in what follows after these definitions is to discuss functorality and one homology sequence, the relative homology sequence, just to show you that there's an extra structure which is very important, which is the change of base points is actually mirrored by a change of algebra and a change of coefficients underlying the construction. And we'll have to look precisely at restriction of scalars and extension of scalars functors between bimodules over algebras to really understand how things are going. So if there's a few questions up to that point, let me stop for a minute. Otherwise, I'll show you the definition details and just show you one homology sequence. No questions so far? Perfect. Okay. So let me just remind you what a path algebra is. So in particular, it's an associative algebra. It's algebraic polynomials. You have or algebras and matrices. You have an R module plus an external multiplication, right? You can multiply polynomials, of course. Morphisms of algebras are just morphisms of modules, so linear maps, which agree with this external multiplication, this algebra multiplication. And which also, so I'm just considering unitary algebras, so I also want to map units onto units. And of course, there's an algebra of paths on precubical sets on any graph and quiver. You look at the underlying R module to be generated by directed paths, zero cube chains if you prefer. And so it's in particular a module, formal sums of these zero cube chains. And then you're going to define an internal multiplication, which is bilinear, generated by the obvious multiplication, which is just concatenation of directed paths. So if you take two directed paths, one from V to W, the other one from Z to T, if they can compose, that is, if W is equal to Z, then you're going just to concatenate the cube chains, okay, giving you a bigger cube chain. Otherwise, they won't compose and you give 0. And that defines an algebra. And you can see that the idempotence, which is of very big interest when looking at algebras and modules of these algebras. So the elements such that E times E is equal to E are going to be the constant paths on vertices. And we would restrict to the rest of the construction to finite precubical sets. Then we have finitely many vertices, and then this will form a unitary algebra. The unit will be the sum of all idempotents. Right? That's classical stuff. And just to show you what they look like, of course, if you take a poset, it's known as an incidence algebra. It's a particular graph, this poset. N is less than n plus 1, and so on, and less than 1. Then if you look at paths, the path algebra, it's just going to be represented by the algebra of lower triangular matrices. Just means that, so R is the ring. You take any coefficient in R in place of this capital R in this matrix, and that's going to be within the path algebra, just because it's going to be the sum of paths. There's actually one generator of directed paths from J to I, where J is greater than I, and there's no generator if J is less than Y. So this explains these zeros here. And you take formal sum, so you can have any coefficients in place of these R's here. And then multiplication of the algebra is multiplication of these matrices. Okay. And when you go from posets to quivers to direct graphs, then you have these matrix algebras where you can have not just copies of R, but for instance, powers of R's, as in that case. Here you have two directed paths from point 2 to point 1. So this corresponds to this entry 2, 1 of this matrix. So you have two generators, that's going to be R2, whereas you have just one generator for paths from 1 to 1, just a constant path. So it's going to be R from 1 to 1 at position at entry 1, 1. And you just have one path from 2 to 2, which is that unique generator here. So multiplications were known, it's a Kunneth algebra. We won't go into that, but that's a particular case of matrix algebras. Okay. So for the examples I had at the beginning, the two holes on the diagonal or anti-diagonal, the ones which are not going to be dihomeomorphic. So you have these two cells, C and D here, and E and F there, but the underlying graph is the same. And the path algebra, as you have 9 points, is going to be a 9 times 9 matrix. And just to show you one entry, so it's going to be triangular, lower triangular again. Just to look at the entry 9-1 corresponds to all die paths. So it's generated by all die paths from 9 to 1, and if you count them, there are 6 of them, right? I, J, N, G, I, H, F, G, and so on. 6 of them, and then you can count each power of R. It's just a number of paths from I to J when you're considering entry IJ within this matrix. Then now from the path algebra, let me see. I can define bimodules on a path algebra. So it's like, well, or modules of this algebra. It's like a module of a ring, right? But it adds on the fact that you have to say what happens with the external multiplication. So if I'm defining a right A module where A is an algebra, I have to say what happens if I multiply two elements of the algebra and then then look at the action of this algebra element onto the module on the right, if it's a right A module. And it's just going to be the action of B on the results of the action of A on X. But for the rest, it's just an ordinary right module on the underlying ring R. Just you have to take care of the algebra multiplication, how it goes, right? And of course, bimodules are just going to be both left and right modules, or equivalently left A times A up modules. A up is the opposite algebra. I'm not going to define, but it's pretty straightforward. The concatenation or the multiplication goes in the reverse way. Okay. So now I can define very easily. I can really very easily see I-cube chains that I had before, not just as modules over the ring, but as modules over the algebra of directed paths. So what you can prove is that the R module we introduced before of I-cube chains, so actually of I minus 1 cube chains, Ri of X, can be given the structure of an R of X bimodule. So R of X is an algebra of directed paths. On top of that, which is going to be very important, it's a free R of X module, bimodule, okay? So it's easy to see. So if you consider I is equal to 0, R0 of X is just R of X, and an algebra is a bimodule over itself, right? And it's a free algebra over itself. It's generated by the identity, right? So at least for this, it's easy. And now for I greater than 0, the action on the left and on the right of a dipath of the algebra R of X is just going to be whiskering. So as I love the term whiskering, I couldn't resist this picture where you have these whiskers of a cat. So here in red, you have typically a 1 cube chain. That's a 2 cell here in red, and you have it whiskered already by these 2 red edges. And you can whisker it to make it a longer 1 cube chain by adding these black whiskers on the left and on the right. That's the operation as an R of X bimodule on 1 cube chains, okay? So it can be defined formally, but it just tells you that you're concatenating the whiskers on the left and the whiskers on the right with the I cube chain you had before. The fact it's free is not difficult to show. It's going to be generated by I minus 1 cube chains that have the first element and the last element P1 and Pn, which are cells of higher dimension, which shouldn't be of dimension 1, which shouldn't be edges. And that's the generators as an R of X bimodule of these I minus 1 cube chains. Okay. So now we could recast the cube chains we had before as not only modules over a ring, but as bimodules over the path algebra. And what you can show very easily is that, and I won't show it, the boundary operator we had before agrees with this path algebra structure, this extra path algebra action. So it's going to be a chain complex of bimodules. So now you can define the homology bimodules, as I told you, looking at the kernel of this boundary operator quotiented by the image. And you just have to be at ease with what submodules and quotient modules are in case you're looking at modules over algebras, right? And not modules over rings. It's not very much different, in fact. So a submodule, R submodule M prime of an A bimodule M. A is an algebra, R is a ring. Is an A submodule if it's stable by the action of the algebra on the left and on the right. It's pretty obvious, right? It's not only a submodule, but it's also stable by the action of the algebra on both sides. And quotient modules of an algebra, it's just the ordinary quotient module definition of the underlying ring module structure, but which has as a bimodule structure the one which makes the projection map, the canonical epimorphism pi here, an A bimodule homomorphism. So it's, as usual, it's basic algebra, right? So, but it's quotient modules and modules exist, and that they are defined that way. And then you can very easily see that the category of modules over a fixed algebra is abelian, indeed, as categories of modules over a ring. Zero objects are just the zero by module. Co-products are just disjoint, are just generated by the co-product over the R modules, and then the algebra structure is just the obvious thing, the different components, right, as it's written here. The kernel of some bimodule map is just the submodule, subalgebra module of x, such that f of x is equal to 0. Exactly, it has the structure of a subalgebra module, of a submodule of algebras. And co-kernels are just going to be quotients of the end, of the codomain over the image of the domain. Okay, as usual, as for ordinary modules of rings. Okay. So now we define, as told you, this. So I call HM of X the homology module of a given precubical set X, sorry, instead of H of X, right? I call this HM of X. This is going to be the kernel of delta over the image of delta on the respective chain dimensional, right dimensional stuff, right? But then you see, I shifted the indexes because when I look at this construction, actually, I'm using die-paths as base elements. So when I'm looking at connected components of die-paths, which is kernel of delta over R0 over image of delta of R1, I'm really looking at something which looks like H1. I'm really looking at the way that two die-paths may be homotopic to one another. So it's really at the level of what is H1, and that's why we changed the index here, okay? But I still have to define HM0, and okay, there are many choices you can make, but the choice I'm going to make is that R0 is going to be as the underlying R module, the one which is generated by pairs of reachable points of X, that is pairs of points X, Y, such that there exists a directed path from X to Y. And the action of the path algebra is just going to, extend this. That is, if Y is reachable from X, then certainly if you have a path from U prime, which is equal to X, to Y, sorry, to V prime, and I have a path from U to V where V is equal to X, then I know that U V prime is reachable. So that V prime is reachable from U because you just compose this path from a path which is the witness that Y is reachable from X with that path. So it's part of this underlying R module, right? And you can see very easily that this is a path, a bimodule over the path algebra. And furthermore, that there's an augmentation from R1 of X, and actually it maps from any Rn of X to R0 of X, where you just take for each cube chain going from V to W, just take VW as a result, and then you complete this by linearity, okay? Okay, so you can define the whole sort of chain of homology modules that way. And what you should understand is that the structure of these homology modules, it's very simple. If you sort of localize these homology modules by taking the action of idempotence on 2 points A and B, so it's localization because when you compute, so EA is a constant path on A, EB is a constant path on B. If you take the action of this on any algebra, on any module of I-cube chains, it will just keep the I-cube chains that go from A to B, right? And it will give you the R module, the R submodule of I-1, actually, cube chains from A to B. So it's some kind of localization mechanism, and this localization for each AB just gives you exactly what Krzysztof Szymanski has been constructing. So it exactly constructs the R module view of things. So between 2 points, the homology of the die path space between the 2 points A and B, which we know thanks to the work of Krzysztof Szymanski is equal to the homology of the directed the topological space of directed paths from A to B. Okay. But then the algebra by module operation from NAB to N A prime B prime just going to be compatible with the class in the corresponding modules. Just going to extend when decomposed right, to extend these dihomotopy class to by pre and post composition by these dipaths U and V, and see where it goes as a dihomotopy class of paths between A prime and B prime. Okay, so the action of the algebra is pretty clear. Okay, and if you look at one simple example, so I told you already about the path algebra. We see this one. Now, if you compute HM1 of X, you have to quotient this path algebra by the image of the boundary map. And the boundary map, there are just two cube chains. One is generated by this cell C, so it's C times any dipath later, plus composition by some dipath after that, and anything which is pre-composed by some dipath. Okay, so you quotient this path algebra by the image of the boundaries of these two one cube chains. And if you look closely what it gives, it's going to, as an R module, is going to be generated by all these elements. And if you are making the calculation, then you're going to end up on this. So just let me show you one thing. The entry 9.1. Entry 9.1 is R3, meaning that you should have three generators three dipaths modular homology, let's say, from 9 to 1. And this is indeed the case, up to homotopy as well, actually, because you just have one class here, 9632, one class which goes through C and D, could be A, I, H, F, G, or K, D, F, G, whatever. They're all homologous, all homotopic, actually. There's one class. And the third class is I, J, L, G. Okay. And this is witnessed by this R3 here. And for all pair of points, you see the number of dipaths modulo homotopy homology in that case that you should get by this very simple algebraic calculation. Okay. Okay, so I'm not going to go much further in these examples. You can ask me if you want to see more. What I just want you to know is in 10 minutes or so is the functorality issues and the homology sequence you have, because you have now to see that we've taken very seriously the fact that we can change base points within the spaces, but we haven't taken seriously yet the fact that we can, what we want ultimately when we want to classify spaces is to change spaces. You want to compare X with Y as spaces. And so is that construction functorial? How can you compare this with this construction? What are the good properties? Yeah, unfortunately, it's not functorial. Okay, you have to be very careful, but you still have enough structure to compare spaces up to dihomomorphism, which is the only thing I want. So what happens when you consider precubical set maps from X to Y? So certainly the path algebra R of X may be not the same algebra as R of Y, except if you are very lucky, right? So certainly the category of modules you're living in when defining these homology modules, it's not the category, the abelian category of modules of a fixed algebra. The algebra may change. So what you really have to consider is the category of modules, or by modules, of algebras with non-fixed algebras. So where objects are not only the module of the algebra A, but also the algebra on which it is a module, okay? And the morphisms from this pair of modules of algebra A to M prime A prime are going to be pairs of morphisms FG, where F is a morphism of R modules, just a linear map, and G is going to be an algebra morphism from A to A prime, such that F of the, let's say, the right action of algebra element A on module element M is going to be the right action of G of A over F of M, okay? This is going to be the sort of change of algebra map, and it has to agree with the action so that define the right sort of transformation of modules of algebras. Okay. Okay, so that's going to be my category of modules of algebras where the algebra is not fixed. And so I won't have time to show it to you, but it's also known. This is not a functorial construction. It's a construction which gives you for any graph or precubical set, the path algebra is not functorial. But if you restrict to cubical maps that are injective on objects, then it's going to be functorial. And as long as you're looking at Mayer-Vietoris, inclusion maps, dihomomorphisms are going to be at least injective maps indeed, then it's enough to have this construction, of course. So this directed homology module construction would be defining a functor from this precubical category with just injective maps to this category of modules of a varying algebra. Okay. And then I have a way to show you that everything will be right up to some twist for getting, I mean, all exact sequences you're used to in homology theory, but with a twist, right? So I'll begin with relative, and I'll begin and end actually with relative homology sequence, but you'll have Mayer-Vietoris, you'll have others, you have a Kunneth formula, which are only proved in some restricted case. I believe this is true in a much more general case, but it's out of laziness that I only prove that. I don't think it's not general. So before getting to relative homology sequence, we have to understand what the change of algebra implies for modules, for categories of modules over these algebras when we change them. And there are well-known functors in algebraic geometry, restriction of scalars and extensions of scalars functors. I'm going to show you, to define to you, and to I will restrict to the particular case where the change of algebras is actually done through an inclusion of path algebras. And in that case, it's very easy to understand, okay? And when I understand these things, it's very easy to define a good notion of relative pair, of directed relative pair. You have to add a small constraint so that you'll have relative homology well defined. So I'll be able to define relative homology, and then I'll be able to have a relative homology sequence almost like the one you know and love, okay? So restriction of scalars, when the algebra is not fixed, what you want to do is, okay, when you want to do is to find a functor from, so you have a map of algebra G from algebra A to algebra A prime, right? And what you want to do with restriction of scalars is sort of restrict A prime modules to be seen as A modules. In some ways, if you think of this map as, it will be the only case in which I'll be using it anyway, as the inclusion of algebra A into A prime, you want to see what happens when you have more coefficients in A prime. You have modules on something where you have more coefficients, and how you restrict them to when you have less coefficients. A is a sub-algebra in that case, for instance, of A prime. It's very easy to define even for general maps, not just inclusions. So G star of M is going to be, as our module, just M, but the action of A or the given element M of capital M. So this A action on the left, A action on the right, A2, just going to be G of A1, so it's an element of A prime, left action on M, and then right action of G of A2, which is an element of A prime, onto this, okay? And because G, of course, map A to A prime, and you have M is A prime module, so you have these operations well defined in A prime, but then you can define this operation A just by, yeah, okay, Pablo, yes, sorry. So it's my 5 minutes, right, or 10 minutes or something like that. Yeah, okay, thanks so much. So 5 minutes before I end, actually. Okay. And then the interesting thing is that restriction of scalars, so this defines a functor. It has both the left and right adjoint. So the left is going to be, it's the extension of scalars, and the right is going to be co-extension of scalars. I'm just going to consider extensions of scalars. So it can be defined pretty abstractly, but then I have no time, so I will just show you what happens when you consider just inclusion of path algebras, right? So now I'm just going to see extension of scalars induced by the inclusion map of algebras, which is given when you have a sub-precubical set Y of capital X. What happens? You have a map, it's an injective, right? This inclusion Y into X. So I have a map of algebras from the path algebra of Y into the path algebra of X. And I'm going to tell you what is this MX thing, which is the extension of scalar of M, of coefficients of M along G. Okay, so if you look at that, okay, I won't show you how it's constructed, but the theorem is that if capital M is a free module, is a free R of X module, a free R of Y module, sorry. So Y is a smaller cubical set. So R of Y is a smaller algebra. You want to extend it as to see it as R of X bimodule. So if M is a free R of Y bimodule, then the extension of scalars to R of X is going to be a free R of X bimodule, freely generated by the same generators as you had before, but with the coefficients you have now, right? So it's the way you understand why it's called extension of scalars, because you have generators of M seen as an R of Y module, but then you want to have extra coefficients, and then you just say, okay, my new bimodule seen as an R of X bimodule. If I have more coefficients, it's just the same generators, but I allow for more general coefficients. Okay, so that's pretty obvious, right? And then this gives rise to a natural relative homology in a very simple setting, because we've seen that these chain complex of bimodules, they're made up of free bimodules of the algebra. So we know if we have inclusion, the relative homology is about relative pairs, about inclusions of space Y into X. So of course, we are almost there with this description. We know how to extend the coefficients to the path algebra of X, given a module over the path algebra of Y, except, okay, it's not quite true that always the extension of scalar of I-1 cube chains on the smallest cubical set Y, so extension to the path algebra of X, it's not always a sub R of X bimodule of Ri of X, because I mean, it is obviously one when you consider I-1 chains where I is greater or equal than 2, because the generators are very simple, and extension will just map to injectively within the larger module with the larger algebra coefficients. But it's not true for the directed path algebra, because directed path algebra, the only generator is the unit, and the units are not at all the same, and it's not going to work. You have to restrict if you really want to have what we want to have exact sequences. And the good definition of relative homology anyway is that this extension of scalars for this cube over Y should be a sub-bimodule of the corresponding cube chains on X. We're not going to have it on the die-paths, except if we are careful. And so the way to be careful, I won't show you the example, but it's that you really need to have just inclusions of cubical sets Y into X, so that it has a directed constraint that if you so Y is a smaller one. If you look at directed paths within X, it can enter Y, which is a smaller piece within X. It can exit it, but once it has exited it, it shouldn't come back to Y. Okay, so there's just, when there's an entry point and it goes out, it shouldn't go back to Y. Okay, and once you have that, which is certainly not the case of this example where Y is just disconnected edges, two disconnected edges. So when you have really something where you go through Y just once, not twice, then the cube chains of y extended with coefficients in R of x is going to be a submodule, a sub-bimodule of the cube chains of x. And then as it's a submodule, you can define the quotient and you can define the homology of the quotient of Ri of x with the sub R of x bimodule, which is the extension of scalars over coefficients on x of Ri of y, and this is well defined. And now if you look closely, and I'll finish here, if you look closely at the extension of scalars properties, it's a left adjoint. It will actually respect co-kernels, and as the construction is a tensor product construction, and as we are only having free bimodules, free is flat bimodules, we'll have extra exactness properties which will allow us to find the right following relative homology sequence, which is almost the one you know. So this is the homology module of the relative pair. This is the homology module we had before the full space. But you have to take the homology module of y, the smaller space, but extended with coefficients in the bigger path algebra x. Up to that point, it's just that's the only difference with the classical one. You have to define this as an exact sequence within the category of modules over the path algebra of x. So you have to extend the scalars for this homology computation for the subspace y. That's the only thing that should do. Okay. And that's not so difficult to prove, and you can do the same thing and compute homology inductively of the directed spheres as usual for the non-directed spheres using this relative homology sequence. Okay, so I'm not going to show you Kunneth formula and Mayer-Vietoris, but up to some point, and if you give some right cover for the various cover notion for the Mayer-Vietoris sequence, you have one. And Kunneth also you have a nice thing. Okay. Again, I'm just concluding on this. So there are many directions from this. One is, do we have an analog of move spaces for the modular homology? So we know that under some conditions, you take an algebra which has nice properties, then there exists a quiver such that, and an admissible ideal such that this algebra will be isomorphic to this quotient of the path algebra of I, and that's sort of the first step of the construction of a move space. And also Christoph Zielinski in the old days showed that between 2 points you could sort of reach any kind of finite simplicial kind of homotopy type. And so it's not far from sort of thinking we might be able to find some sort of more space construction. Maybe it's not true in general with that restricted construction, but at least it gives some indication we're not too far from something general now. I haven't developed the real link to persistent modules, but there are particular cases of persistent modules, indeed. And I'd like to develop from invariants and barcodes for these precubical sets. The filtration is some kind of fairly complicated filtration of pairs of dipaths, so it's much more complicated than even multidimensional persistence. So it's some kind of poset or category persistence in general. Then there are links I'd like to make with homology of monoids and rewriting. The construction is very close to some construction that Groves did, for instance, on algebras of monoids and so on the homology of monoids based on modules of the algebra of the monoid. So it's very intriguing to me. And I like also to be able, if I can generalize this enough, to really apply this to actual differential inclusions and try to find finer invariants than the ones with ordinary homology for classical Conley index. So using directed homology instead of classical homology. And as we have relative homology, we're not too far from being able to define these these Conley indexes as some relative homology elements, let's say. Okay, and then also, as you see, what I use to have these exact sequences is basically a local abelian structure plus some sort of functors that change coefficients, which have nice exactness properties, and that's been considered in this area framed by categories by Mike Schulman, and I'm pretty sure we can sort of find the sort of axiomatics that would sort of be not a part of Freud's characterization of abelian categories. So sort of locally abelian categories, I need to have these exact sequences. I think they can be linked to these framed by categories. Okay. So I'm going to stop here, and thanks again, and please ask any questions. I've been a bit too long, sorry.
Okay, let's thank our speaker first. And do we have any questions for Eric?
It's been so long, and sorry about that.
I do have one question. So
Yes.
with this construction, for example, the case for S2 that you show that the homology is different from what we're used to. So
Yes. Yeah.
So some of the first consequences of like once you learn homology or like fixed point theorems or things like that, are there any of those which translate to counterintuitive fixed point theorems?
Yes, so that's a good question. I like to have some fixed point theorems with this homology. For now, I don't have, but for sure we would like to have some sort of index notion of some kind and whatever. So I would think, of course, the trick is that you always have some ways to transport classical theorems from the die path space to the directed space somehow, because we're taking classical homology of the die space, right, as a base elements. So as we have classical homology of this die path space, we have also some index notion of functions lifted to path spaces. We'd have like Lefschetz's fixed point theorems on this die path space. So a good, an easy way to have some sort of fixed point theorems would be to say, okay, I will have some sort of fixed point in the die path space, whatever that means for the directed space, right? But probably you don't want exactly that. Probably you want fixed points of real maps on real points, not on paths, right? And there I don't know how to do this, because for now this is fairly restricted in the sense that the theorems I have on the exact sequences, they're going to hold for quite simple cubical sets. I didn't show you exactly what are the axiomatics, the ones that Christoph Ziemanski used to have this correspondence with the die path space. You have, I mean, you won't reach all sorts of spaces you'd really like to talk about, but still in that restricting framework, that would be interesting to look at. So, yeah.
Any other questions for Eric?
I have one question.
Yes.
I was late, so I don't know if you say this before, but do you know the simple modules of your algebras?
So sorry, I didn't hear you.
Sorry. Do you know the simple modules of your algebras?
Yes, sort of. Yes. Yeah.
Okay. What
But maybe.
how can you describe them?
Oh, yes, it's a good point. It's a good question. I haven't looked into that. So of course there's quite a lot which I didn't speak of, which links to ordinary classical persistence theory, which is looking at as a representation. So the correspondence between representation of some quiver, some some quiver with these bimodules of the path algebra. Which quivers are we looking at? And so then what sort of the composition of this representation we can have for this class of cubical sets, which have also restricted underlying quivers. So what should be simple algebras and so on. So I don't know, but there are first steps towards looking at the composition of these representations, which are wide anyway. I mean, there's no way there's going to be very good description. It's even worse than multidimensional classical multidimensional questions. But yeah, there's some amount of work that should be done that's not there yet. Does it answer your question? Yeah.
Yeah. It's I know it's a big problem to describe the simple modules over any explicit algebra. So a category of modules. So yeah. Well, thank you.
Yep.
Okay. I think we can thank Eric again.
Thanks a lot. Thank you.